Section 9.1, Molecular Shapes. In Chapter 8, we use Lewis structures to account for the formulas of covalent compounds. Lewis structures, however, do not indicate the shapes of molecules. They simply show the number and types of bonds between atoms. For example, the Lewis structure of carbon tetrachloride tells us that 4 chlorine atoms are bonded to a central carbon atom. The Lewis structure is drawn with the atoms all in the same plane. As shown in Figure 9.1, however, the actual three-dimensional arrangement of the atoms shows the chlorine atoms at the corners of a tetrahedron, a geometric object with 4 corners and 4 faces, each of which is an equilateral triangle. The overall shape of a molecule is determined by its bond angles, the angles made by the lines joining the nuclei of the atoms of the molecule. The bond angles of a molecule, together with their bond lengths, accurately define the shape and size of the molecule. In carbon tetrachloride, the bond angles are defined as the angles between the carbon-chlorine bonds. You should be able to see that there are 6 carbon-chlorine angles in carbon tetrachloride. They all have the same value, 109.5, which is characteristics of a tetrahedron. In addition, all 4 carbon-chlorine bonds are the same length, 1.78 angstroms. Thus, the size and shape of the carbon tetrachloride are completely described by stating that the molecule is tetrahedral with carbon chloride bonds of length set 1.78 angstroms. In our discussion of the shapes in molecules, we'll begin with molecules and ions that, like carbon tetrachloride, have a central atom bonded to 2 or more atoms of the same type. Such molecules conform to the general formula AB to the N, in which the central atom A is bounded to N number of B atoms. Both carbon dioxide and water are AB2 molecules, for example, whereas SO3 and ammonia are AB3 molecules, and so on. The possible shapes of ABN molecules depend on the value of N. We observe only a few general shapes for any given value of N. Those completely found for AB2 and AB3 molecules are shown in Figure 9.2. Therefore, an ABN molecule must be either considered linear, with a bond angle of 180 degrees, or bent with a bond angle not of 180 degrees. For example, carbon dioxide is linear, and sulfur dioxide is bent. Figure 9.1, Tetrahedral Geometry. A tetrahedron is an object with 4 faces and 4 vertices. Each face is an equilateral triangle. The geometry of a carbon tetrachloride molecule. Each carbon chloride bond in a molecule points towards the vertex of a tetrahedron. All the carbon-chlorine bonds are the same length. All of the chlorine bond angles are the same. This type of drawing of carbon tetrachloride is called a ball and stick model. And C, a representative of carbon tetrachloride, is called a space-filling model. It's shown the relative sizes of the atom, but the geometry is somewhat harder to see. For AB3 molecules, the most common shape places the B atoms at the corners of the equilateral triangle. If the A atom lies in the same plane as the B atoms, then the shape is called trigonal or planar. If the A atom lies above the plane of the B atoms, the shape is called triagonal pyramidal, a pyramid with an equilateral triangle at its base. For example, SO3 is a trigonal planar, and NF3 is trigonal pyramidal. Some AB3 molecules, such as chlorine trifluoride, exhibit more unusual T-shape, shown in Figure 9.2. The shape of any particular ABN molecule can usually be derived from one of the 5 basic structures shown in Figure 9.3. Starting with a tetrahedron, for example, we can remove atoms successively from the corners, as shown in Figure 9.4. When an atom is removed from one corner of the tetrahedron, the remaining fragment is a triagonal pyramidal geometry, such as found for NF3. When 2 atoms are removed, a bent geometry results. Why do so many ABN molecules have shapes related to the basic structures in Figure 9.3, and can we predict these shapes? When A is a representative element, one of the elements in the S or P block of the periodic table, We can answer these questions by using the valence shell electron pair repulsion, or VSEPR model. Although the name is rather imposing, the model is quite simple. It has useful predictive capabilities, as we'll see in section 9.2. Figure 9.4, derivatives from the ABN geometries. Additional molecular shapes can be obtained by removing corner atoms from the basic shapes here shown in figure 9.3. Here we begin with a tetrahedron and successively remove corners, producing first a triagonal pyramidal geometry and then a bent geometry, each having ideal bond angles of 109.5. Molecular shape is meaningful only when there are at least 3 atoms. If there are only 2, they must be arranged next to each other, and no special name is given to describe the molecule.